My name is Michael Messere. I'm a grad student at Columbia University. And I guess initially I was going to talk about the Milky Way galaxy, but instead I'm not. I'm going to talk about much smaller things. And so I'm going to be talking about recent work I've been doing with Greg Bryan on high specific energy supernovae feedback in dwarf galaxies. All right, so I'm first not going to talk about dwarf galaxies. I'm going to talk about more massive systems, where the black holes are thought to be the primary feedback mechanism that regulates star formation in these systems through preventative feedback. And what I mean by preventative feedback is that gas accretes onto the central black holes in these systems. It heats up the surrounding medium, whether that be the CGM or the ICM. This prevents gas falling into the halo. And then after some time, after some cooling, then this gas then precipitates back onto the central black hole, and this cycle repeats itself. And this baryon cycle is primarily driven by this simple ratio of the cooling time to the freefall time. Where a value of 10 or greater, we say that the system is radially stable, it won't collapse, and otherwise if the value is smaller than 10, it's radially unstable and it will collapse. And so I'll kind of get to it later on, but this somewhat has to do with what we think goes on in the CGM of dwarf galaxies. So now dwarf galaxies. So at the lowest end of the mass regime, these systems we think are quenched due to ionization in the early universe. However, if you go to a bit more massive system, say around 10 to the 10 solar masses, we know that supernovae are the main source of feedback. And what's super unique about dwarf galaxies is that A, they have no AGN feedback, so we don't have to worry about that. Two, or I said A, so B, there's no virial shock. And also C, they have very shallow potential wells, meaning that when metals, when energy and mass are ejected from the ISM, they end up in the CGM, meaning that these systems, or specifically the CGMs, are very sensitive probes to the underlying feedback mechanisms that we feed into our simulations. All right, so it turns out that if you look at, say, cosmological simulations, there's a bit of a discrepancy between their CGMs. So what this plot is showing, it's from a recent review article, is showing the CGM mass fraction as a function of halo mass. And so we don't have to worry about the high halo mass regime where things tend to agree. But if you look at, say, the dwarf galaxies, around 10 to the 11 solar masses or so, we find that in some simulations, there's a ton of baryons in our CGM. So the y-axis is just the baryon content normalized by the cosmic baryon fraction, where in other simulations, there aren't a lot of baryons in the CGM. And so in some of these systems, say in TNG, they implement more of an objective feedback mechanism, meaning that material falls into the ISM, and in order to stay on, say, the stellar mass-halo mass relationship, this material is then removed from the ISM, meaning that you have a very high mass loading factor. Whereas in, say, other simulations like Eagle, you have more of a preventative feedback mechanism. And then another interesting thing, if we think about systems around 10 to the 10, 10 to the 11 solar masses in terms of their halo mass, is that at the peak of the cooling curve. And so this means, if we look at the newest high-resolution J-produced image of the galaxy, we have the supernovae feedback going on in the center at the ISM. We have the CGM, we have the IGM. Of course, we have IGM accretion. We have fountain flows from the ISM back into the CGM, into the ISM. Then we have winds being blown out into the CGM. And so in our traditional picture of a dwarf galaxy, we're at about 10 to the 10 solar masses. They're at the peak of the cooling curve, which means that if we heat up the CGM, we expect this gas to cool quite quickly. The ratio of the cooling time to the freefall time is a bit less than 10, meaning it's radially unstable. Material falls back into the ISM, and we have to have high mass loading factors in order to remove this material out of the ISM. And so one thing that kind of contradicts this picture of dwarf galaxies is that through recent observations, these high-resolution patch simulations, like the Tiger suite of simulations, and also gas regulator models, we know that dwarf galaxies tend not to have high mass loading factors. Their mass loading factors tend to be on order 1 or so, depending on the system you look at. And so what we suggest is more of a preventative feedback model in these dwarf systems. So what this means is that you have high specific energy winds flowing from your supernovae in the ISM into the CGM. These high specific energy winds shock heat the surrounding CGM. And the key to this model is that it's able to sustain the CGM at approximately the virial temperature such that it's not really cooling. And because it's not really cooling, you're able to be in a radially stable regime where the freefall or the cooling time to the freefall time is a bit more than 10, and therefore you don't need a high mass loading factor to remove this gas out of your ISM. Yeah, and so this is very similar to, say, the cluster picture that I brought up in the beginning. And so my research is interested in A, does this preventative feedback operate in dwarf galaxies? And also, if this is the case, B, how does it operate and reshape the surrounding CGM and the IGM? So I do this by running cosmological zoom-in simulations using ENSO. So I select a sample of 9 galaxies, trace them back to a redshift of 100, run them back to a redshift of 0, and look at their properties. This is kind of the distribution of the sample of the, I'm interested in things that have a virial temperature around 10 to the 5, meaning that their virial radius is around 100 kiloparsecs or so. These are all isolated dwarf galaxies, and this is kind of just a slice plot of one of them showing, say, the density distribution, the pressure, metallicity, the cooling time, and this is like a 10 by 10 RVR image. And so there's kind of 4 simple results from our work so far. The first one is that, yes, the CGM, and actually beyond the CGM, is able to be sustained at the virial temperature. So this is a slice plot looking at temperature edge on the galaxy, where this is the ISM, a tenth of the virial radius, and this is 1 by 1 RVR. And so this is also the temperature that's normalized by the virial temperature of the system. So you can see that the CGM is quite hot. And we can also zoom out to, say, 20 by 20 RVR, and even out to, say, 5 or so RVR. We're still being able to have these wind-induced shocks are able to heat the CGM to about the virial temperature. And so this is preventative feedback, where we're preventing IgM gas from accreting onto the CGM. Then also in another scale, where we're able to heat up the CGM such that the CGM gas doesn't accrete onto the ISM. Cool. Number 2 is that we can look at the high specific energy winds of these systems. And so this is just a function of redshift from, say, a redshift of 3 to the present day universe. And we're separating out the cool wind versus the warm hot wind. And we find that the hot wind has a specific energy around 100 to 1,000 times greater than the cool wind. And this just means that the hot wind is able to reach much further out and is able to heat and expand the CGM, the gas, to prevent it from falling in, and to prevent the gas from the IgM from falling into the CGM. And then we can do a few other things. So say we can measure the mass inflow rates, mass outflow rates at the ISM CGM boundaries. We can also measure the energy loading factors, the mass loading factors. And in the interest of time, I won't go into these in detail, but essentially what we find is that you prevent about 75% of your mass from falling into these dwarf galaxies. The mass loading factor of these systems tend to be on order of 1 to 10, and also in terms of an energy loading factor, about 10% of the available supernova energy in the ISM finds itself or escapes into the CGM. Result number 3 is that we look at the cooling time evolution. So this is now the cooling time to the freefall time as a function of fraction of virial radius out to 2 RVR. And so ignore the red and blue lines, but essentially if we look, the red and blue lines are just the example of one galaxy's evolution through redshift, but I've binned the sample in terms of redshift. So the dotted black line are systems early in the universe between a redshift of 2 and 3. And we find that the ratio is quite low, meaning that these are radially unstable, things are collapsing in. But as a function of redshift, if we then go to the present day universe, we find that outside of the immediate ISM, say 20% of the virial radius, that in the CGM, the ratio is boosted well above 10, meaning that our system is radially stable, and we prevent collapse further into the ISM. And result number 4 is this thing called the closure radius. And so this was essentially, if we naively expect that, or I guess naively we expect that if we take the halo mass and multiply it by the cosmic baryon fraction, this is the amount of baryons we expect in our CGM. But we know that feedback redistributes these baryons, so we don't expect 100% of our baryons to be within the dwarf galaxy RVR. And so instead we can play a game where we go from the center of our halo and we move slowly outwards until we recollect our missing quote-unquote baryons. And so it turns out in these dwarf galaxies, you have to go to out to about 15 RVR or so to recollect your missing baryons. And this is kind of in agreement with a recent paper where they did this in TNG, as well as 2 other cosmological simulations, where they find that at least the low mass regime, this is around between 10 to 20 or so. And so this is again just showing that we're really having this preventative feedback at play. We're preventing all the baryons from falling in the first place. Yeah, and then these are just my summary. And then in terms of future work, kind of there's a lot more things I could do. I'm interested in following the exact gas flows by placing tracer particles in my simulations. And also, I really haven't thought much about observational tests of this, so it'd be interesting to think more about, say, metal content in the CGM and in the IGM, specifically, say, tracers like oxygen-6 that are following this warm, hot gas phase. Thank you.
That last thing on the closure radius, 15 RP, do the metals propagate out that far? And if not, then what is doing the prevention? The metals or the tracers of outflows?
Yeah, so I haven't looked specifically at what the metal content is of the gas that far out, but because we know that, like in these high specific energy winds, it's mostly through the hot winds. These hot winds are going to be from the supernovae, and the metals are going to be from the supernovae. So I'd expect that the metals are going to be that far-reaching. Although that's one thing I haven't plotted, is I haven't looked at all about, say, the metallicity distributions that far out.
Yeah, Scott. How much mass is out there around this galaxy? What sort of fractions of the gas is a function of radius?
Oh, so like the CGM mass?
Yeah,
say?
of these smaller galaxies.
Yeah, I'm not sure as well, but like in this plot, so again, I mentioned that we prevent 75% of the gas from falling in. So I guess if you take the halo mass of 10 to the 10, multiply by 0.16, and say that 75% of it's prevented from falling in,
okay.
That's the mass. That is
All right, I'll
that.
figure it out. In the back.
Yeah, I was curious about when you showed the picture of the temperature of the CGM. A lot of it was near the virial temperature that you were talking about. But I was curious kind of about the cooler component, like closer to terminal 4. Have you looked at that much?
So in this slice, the cooler component is the ISM, but if we move out, this is the IGM. So my guess is you still see, so this isn't a filamentary feature, although it does fall along a filament in the simulation. I'd say that it could be the scaling of the color bar I used, but this is likely previously shock heated at an even higher redshift that's cooled off, because it seems to at least follow kind of the structure you'd expect from supernovae in terms of like being like spherical-ish. But I haven't thought too much about kind of the cool gas evolution very far out as an option of time.
Jesse.
Sure. If there's so much high specific energy wind in dwarf galaxies, can you convert that directly into a luminosity of H alpha emission you'd expect from something like Dragonfly spectral imager?
I suppose you could do that, yeah. It's something I haven't done, but that'd be interesting to do. Also in terms of like X-ray predictions, things like this, of how hot the halo is.
All right, we have time for one more question.
Thank you. I wonder, like, how you define the supernova explosion rate inside of the galaxy, or like it's a range, or how do you decide that?
Yeah, so this is something I completely glossed over, which is the feedback mechanism itself. And so this has gone into more detail in this paper from Nathan Goldbaum from a few years ago. But essentially, how it's done in this simulation, as well as most simulations, is you say that if you have 100 solar masses, there's about one supernova that goes off, which with 10 to the 51 ergs of energy. And in this simulation specifically, it's through ENSO, so it's grid-based. And so this is essentially, we put momentum into the surrounding 27 cells or so. Then this difference in kinetic energy is subtracted off from our total of 10 to 51 ergs. And this difference is then a thermal dump in the host supernovae cell. And so this then will vary a lot on like resolution that you achieve in like the ISM. And so, yeah, so definitely that's how it's done. Yeah, to answer your question.
Thank you.
All right, let's thank Michael again.